This is a video on the fundamental counting principle. I've shortened that over here to be the fundamental counting principle, just FCP. So imagine a situation. We're going to go to brute force over here. Brute force method of finding the sample space. Okay? And again, omega is just a Greek letter. It represents sample space. So if I was trying to figure out how many combinations or how many ways, how many outcomes are there of having 3 choices for bottoms and 2 choices for tops. So we're looking at jeans, shorts, and dress pants, and then t-shirts and polos. So you have to choose one of each of, so one from this group and one from that group. So I'm going to shorten them. So then I have to keep writing. It's a little bit better than what it could be. So J, S, and D, and then T and P. So we need one from each group. So the brute force method has some value. And when there's only so many options, you literally can say, okay, I need jeans with a t-shirt, and I need jeans with a polo. I need shorts with a t-shirt. I need shorts with a polo. I need dress pants with a t-shirt. I need dress pants with a polo. And I've exhausted all of the choices. Now, brute force, it didn't really take a long time, but that is the entire sample space. So there are 6 items in that sample space. Option 2, the fundamental counting principle says, well, let's take the number in this set, and let's take the number in that set, and let's multiply them. 3 times 2 gives us 6. And all of a sudden, we have the number of values within that set. Okay, so the sample space has 6 items. That is the beauty of the fundamental counting principle, especially when you consider a situation like this. Let's say we're going to a restaurant, and we let's call it our favorite restaurant, and we know that for appetizers, there are several options. You could do soup, you could do salad, you could do wings. Good thing I just ate lunch. You could do potato skins, or you could do nachos. Actually, I guess you could also do done. You don't really need. So then you can go to a main course. Let's just say that there are sandwiches. Let's say there's sandwich 1, sandwich 2. You could do pasta dish. They're really generic. You could do pizza, or you could do chicken. Really simple. You really have to have a main, or they'll kick you out. I don't know why. And of course, the dessert, you could do pie, you could do ice cream, you could do cake, and also you could do none. Now imagine writing out all the combinations. Okay? I mean, you could look at maybe an example of an outcome. Might be soup, pizza, and pie. That is one outcome. But this is really about the fundamental counting principle. So all we really need to know is how many are in the sample space. So the number in the sample space is going to be equal. Well, let's see. There's 1, 2, 3, 4, 5, 6 options for appetizers. 1, 2, 3, 4, 5 options for a main. And then dessert, there are 4. So in order to calculate the number in the sample space, 6 times 5 times 4, 30 times 4 is 120. So at this restaurant, just using those options, it's obviously imaginary, there are 120 options for outcomes. And that's a quick way or a quick use of the fundamental counting principle. Just tally up each group, multiply them together, and you have your answer. Let's just do one more, a little more practical in terms of probability. We'll do 2 actually. So here's another example. A very common probability experiment is to roll 2 dice. We'll call them 6-sided, and we'll call them fair. Both of those are important. 6-sided gives us how many options there are. Fair tells us that each of those 6 sides is equally likely. So you have, and we probably should also say that they are distinct. The fact that they are distinct means you can tell the 2 dice apart, and that a 4 on one is different than a 4 on the other. So for example, you might have die number 1 is a white die, and die number 2 is a pink die, so that you can compare them and see the difference. So if we're just looking for sample space, there's 6 times 6, or 36 different options. Now, I really like to see all those options, so I've come up with a nice graphic organizer for this, and it looks kind of like this. So we do 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6. And I'd make basically a grid, and I put a dot, and each of those dots represents an outcome. And so we basically have something like this, where we can group all of them like that, and then straight vertically downward. Oh, that's not straight down. So basically, this dot right here would represent the combination of 5 on one and 3 on the other, which is different than 3 on one and 5 on the other. They represent different outcomes. So that's just a visual of what the sample space would look like, and the number is 36. A couple more quick ones. Let's say we had an experiment where we were flipping a coin and spinning the spinner from the game of Life, which if you've never played, you really should. And just so you know, it has 10 numbers, 1 to 10. Okay, and we all know coin toss is heads and tails. It's a fair coin. And let's also roll a 20-sided die. So, fundamental counting principles. How many are in omega? Well, there's 2 here, there's 10 here, there's 20 there. And if I multiply 2 by 10 by 20, 2 times 10 is 20, 20 times 20 is 400. So there's 400 different ways of doing all 3 of those things. You could do heads with a 1 and a 1. You could do heads with a 1 and a 2. You could do heads with a 1 and a 3. You could do heads with a 1 and a 4. And if you did the brute force method there, it would take you a great amount of time to gather all